Welcome back. So, we are going to now look into the design of individual modules. In the previous sessions, we have looked at the high level specifications and we tried to arrive at the specification of the front end amplifier also, looking at the signal characteristics and the electrode characteristics and so on. Now, based on that, now our next step is to go deeper into each of these modules one by one and consider the topologies, the analysis and design steps, and finally, the transistor level design to meet the specification that we have arrived at in the very beginning. So, let us now look at the amplifier that we are going to use. So, we have the input signal specifications known, and the very first thing that we have determined is the requirement of input impedance, and that would imply something when we go for the choice of the feedback topology. So, we know that why do we use feedback amplifiers, because we need a well defined gain in our circuit, which is very well controllable and defined using feedback parameters. We know that the gain of active amplifiers, active load amplifiers like differential amplifier with active load or two stage operational amplifiers can be pretty high. The open loop gain can be several tens of thousands, it can be even up to 10 to the power of 7, 10 to the power of 8 if you are designing the integrated circuit properly. So, the design requirement will of course depend upon the overall specification of closed loop gain, etc. But in order to get a well defined gain, we rely on the feedback operation. We obtain a gain approximately equal to 1 upon beta, where beta is defined by the feedback factor, and that is mostly determined by the feedback components like resistors or capacitors and their ratios, which does not change significantly from process to process or does not change significantly over time. So, that ratio is a stable or relatively much more well defined and precise quantity. Therefore, we take the advantage of feedback to build our front end amplifiers. Now, there are different ways of implementing feedback. You can have an inverting configuration, non inverting configuration, you can have resistive feedback, capacitive feedback. So, the first answer you would like to have is what kind of feedback topologies to choose and what kind of amplifier to choose, whether it should be single ended output or fully differential output. So, those are the questions that we would need to answer, and then secondly, what should be the number of stages for the amplification, how much amplification should be there in the first stage, how much amplification should be there in the subsequent stages, and so on. So, these are the high level answers. So, we need to see what is the feedback scheme, whether it is going to be resistive, whether it is going to be capacitive, whether it is going to be inverting or non inverting. So, we need to answer these, then we need to see the number of stages involved, gain of each stage. We need to see whether we need to have a fully differential or differential to single ended topologies for our amplifiers. These are the questions that we would like to answer. So, the last question is, I would say, easiest to answer, whether we want to have a fully differential implementation or differential to single ended implementation. So, the trend is that for integrated design, especially for low power applications where you are having external electronic interface, the choice for fully differential operation dominates. That is more acceptable topology, because fully differential operation, as we know, it can be more robust at every stage. So, we keep the signal differential all throughout the signal chain. So, if I revisit my circuit over here, so if you see the output also I have done it differentially. So, the input is taken differentially, you have two ports for the input, and effectively you are processing the difference between the signals recorded from these two electrodes. But even after the amplifier, I have put two outputs. So, basically it is a differential amplifier with differential output. So, it is a fully differential amplifier with differential input and differential output. Even the filters circuit that we will be having will keep it fully differential, so that even after the filter the signal that is going to the ADC can be fully differential. Even the A to D converter can be constructed in a fully differential fashion. The advantage of fully differential operation is that at any stage, if there are common mode noise sources coming from different sources like the supply or the clock signals that you are having in the vicinity of the analog circuits, the overall analog domain processing can be immune to that. So, especially as we are moving towards mixed signal integration, as more and more analog and digital functionalities are getting integrated on the same die, on the same chip, the possibility of corruption of analog signal through multifarious analog signal, digital signals coming in the vicinity can become even stronger, even worse. As a result, I would like to maintain the fully differential operation even till the last stage, so that even the ADC can be operated in a fully differential mode, and finally, the digitized signal enters into the DSP domain or digital signal processing domain, which is immune to those kind of noises. So, even though the input, for example, may not be having so much large noise sources or common mode noise sources, the VDD noise is the only noise of concern maybe for the input stage. But if you go deeper into the circuit, ADC is a block which is a mixed signal block, which is sitting very close to digital circuits. It may be operating with lot of clocks. So, as we will see in the design of the ADC, in general there will be a lot of digital circuitry, control circuitry sitting in the vicinity of the ADC. And whenever there is a digital circuitry, it is having a lot of switching between zeros and ones. You have a high frequency clock and you have a digital data coming out, and subsequent stages you are having digital signal processing, and there is going to be some kind of control which is coming from those blocks back to the ADC, and all that digital switching can produce lot of noise. And although in power management people generally take care of that by isolating the power supply of the analog domain and the digital domain, you have a common substrate. You are going for a mixed signal design where you have a common substrate, and in general the capacitive coupling between those digital signals and the substrate that will propagate noise along the analog part of the design as well, and as a result there is a high chance that the ground and the VDD will also have that kind of noise coupled with them. Along with that, you have digital signals or metal lines carrying those strong digital signals in the vicinity of these analog processing block. They can also interfere with your analog processing chain. So, as we are going closer to the digital domain, the noise contributed by those digital components sitting close to this ADC is even stronger. As a result, the amplified signal also has a good chance of getting corrupted because of that common mode signal produced by this very strong digital signals having peak to peak swing close to VDD swing. As a result, it will be advantageous to keep this entire operation differential, so that even the filter stages and the A to D stages are operating in a fully differential fashion. So, this answers our last question, whether we want to have a fully differential operation or a differential to single ended. One topology would have been that we can use our differential amplifier topologies where the input is differential, but the output is single ended. So, we will see that there are topologies of course which are having differential to single ended amplifier being used, and in that case, although the amplifier is rejecting any common mode noise at the input, but after that it is giving out an single ended signal, and therefore, within the chip you can have common mode noise which can influence that signal. To avoid that, I would rather go for a fully differential operation, so that the front end amplifiers, filters up to ADC all are fully differential. Now, let us go to the first question, which is the feedback scheme. What kind of feedback scheme are we going to use? So, if we are looking at fully differential signal, suppose this is the positive input and the negative input, corresponding to that you have the negative and the positive outputs defined over here. That means, if the input over here goes high, this particular output goes low. So, it is relative, right. So, if we want to define, if we ascribe a definition of positive and negative to these two terminals, corresponding to that we have to look at the differentiation of positive and negative at the other two terminals. So, if the circuit is such that this terminal signal going up pushes the signal at this particular terminal low, that means with respect to this positive terminal, this is a negative terminal. So, that is how I am defining or assigning these positive and negative signs to this. We will see at circuit level how do we do that. Now, here if we want to implement the feedback operation, the inverting configuration is convenient to implement. So, if you look at the corresponding single ended version, this is the single ended version for the inverting amplifier. We can put R2 and R1, as a result we get a overall inverting gain of minus R2 upon R1. This can be implemented much more conveniently in this fully differential operation. However, if we look at say non inverting configuration, where you are having the input signal applied at the main input and you are having the negative feedback coming at the inverting amplifier, here there is a interaction between the single ended output and the negative input, that will be difficult to implement using this topology. So, the fully differential amplifier will be amenable to an inverting amplifier design, therefore, we will choose the inverting gain topology, and therefore, we can envision the impedances in the feedback network, let us call it Z2 and Z1. Likewise, on the other side also we can have the impedances connecting the positive output to the negative input, same value Z2 upon Z1. So, this basically means that you are having VO plus and VO minus, this is your V in plus and V in minus, and the overall relationship between VO plus and VO minus, V in plus and V in minus can be expressed as VO plus minus VO minus upon V in plus minus V in minus is going to be R2 upon R1. So, this is the way we have defined it. So, if the signal over here goes up, the positive terminal over here should be going up. So, overall if this is the definition, we can say that the overall gain from the differential input signal, that is V in plus minus V in minus to VO plus minus VO minus, is going to be defined by Z2 by Z1 to be more precise in this case, because we have defined the impedances as Z2 upon Z1. Now, let us look at the other question, how do we implement this Z2 and Z1. So, there comes the requirement of the impedance value. So, what we have seen is the input impedance required is very large. So, you can based on whatever we derived on the first sessions, we require an input impedance of more than 10 mega ohm, and in this differential amplifier topology we know that what is the input impedance. So, if we recall our discussion on a single ended version, how do we find out the input impedance of this feedback amplifier? So, we say that this is an AC ground, that means this is at a DC potential, and in terms of AC this is at AC ground, and if the amplifier gain is large, we say that this is also going to be almost at a similar potential, this is also going to stay close to this AC ground. As a result, if I am applying an input signal over here V in, this terminal almost acts like an AC ground, therefore, the input impedance is nothing but R1, or in terms of impedance, if I look at this particular circuit, the input impedance in the positive terminal is Z1, in the negative terminal also Z1. Therefore, if I look at a differential source, suppose there is a differential source, I am defining the source as V in plus minus V in minus, overall it is experiencing Z1 and Z1 between these two AC grounds, which are supposed to remain close. So, these two signals, these two values will remain very close, that is what the amplifier is going to enforce. Just like in the single ended version, the amplifier enforces that the positive, this terminal over here, which will remain very close to the inverting terminal, the signal levels over here, the potential over here will remain very close. Likewise, in this fully differential scheme also, the high gain of the amplifier from this input to the output will ensure that these two voltages, these two signal levels remain very close, they are going to follow each other, and as a result, if I look at the two inputs which are remaining very close and remaining close to AC ground, as a result we can say that the input signal V in plus minus V in minus is experiencing an overall impedance of 2Z1 looking into the amplifier, and therefore, if I want to have a very large Z1, that would mean I need to have a very large value of R if I am implementing it with R, and if I do that, one of the most important criteria that will be conflicting with our requirement is the noise. We know that the noise of a resistance is proportional to the R value, the mean square noise value is proportional to the R value. Therefore, if you are putting a large R over here, it can lead to very large noise contribution by that R to the input signal, and it can completely corrupt the input signal. Therefore, we cannot possibly go for a very large R value. The other thing is that if you use a large R over here, maybe 10 mega ohm, and you are trying to build a gain of at least 100 in this stage, that means here this one will be even larger. And for 10 mega ohm, you will need 1 giga ohm over here to get a 100 gain. So that will also create difficulty in realizing the feedback with accurate enough values or accurate enough ratio of R2 upon R1. So these two factors will make the choice of R as the feedback element to be a bad one. So rather than that, we would go for capacitive feedback. So we can choose the Z1 and Z2 as capacitors, so that the overall gain Z2 upon Z1 is determined by the capacitance ratio. So rather than going for resistor, we will put capacitance C1 and C2 over here, and we know that in that case the ratio Z2 upon Z1 will be given by C1 upon C2, 1 upon SC2 divided by 1 upon SC1. So in that case, we can have the value of C1 as the larger one, C2 is going to be the smaller one, and the overall ratio will be determined by the overall gain will be determined by the ratio of these two. Second point is input impedance in that case. So because the resistive element has been eliminated, you have only the C1 coming into picture from the input to the inverting and non-inverting terminals. So the effective input impedance will be just given by 1 upon omega C1 at those frequencies, and if the C1 values are small enough, the impedance at the desired frequency can be sufficiently large. For example, if I assume typical C1 values of few picofarad within 10 picofarad, within the desired frequency range, the input impedance can be pretty large. So that small choice of C1 will ensure that my input impedance is above a desired value and signal is not getting attenuated, and therefore we are going to stick with the choice of C1 as the feedback element. So let us continue with this discussion and go deeper into the design of our front-end amplifier step by step by discussing the transistor level design and the analysis involved, arrive at the specification, and then go for transistor level sizing gradually.